Thank you, Noga. It's a pleasure to be back at the IES in Princeton. Thank you for inviting me, Noga. So Ramsey theory consists of a large body of deep results in mathematics that say that every very large system contains a large, well-organized subsystem. And how very large you need to get a certain nice pattern, a nice well-organized subsystem, is quantified through Ramsey numbers. So I'll talk about a survey on some recent results and problems on Ramsey numbers. Here's a classical definition. The Ramsey number Rk of n is the minimum big N such that every two coloring of the k sets of an n set contains, so big N set contains a monochromatic little n set. That is, you have a big set n, and you look at all the k tuples, all the subsets of size k, and you assign it one of two colors, red or blue. And this is the Rk of little n, the minimum big N, such that no matter how you two color all the k sets of the big N set, there is going to be a little n set, all of whose little k subsets are the same color. Now, classical bounds for k equals 2, this is coloring the edges of a complete graph if you want a complete monochromatic subgraph. Our R2 of n is at most 2 to the 2n. And this is a nice pigeonhole argument by Erdős and Szekérys. And the lower bound is a very influential proof of Paul Erdős from 1947 using the probabilistic method. So this is Erdős and Szekérys. Is the upper bound in Erdős from 1935 and 1947. Erdős gave this lower bound. The fact that these numbers even exist was proved by Ramsey in 1930. And despite a lot of attention, these exponential constants have remained the same. So there's been a little bit of progress on both the upper bound and lower bound. The most substantial progress has been in the upper bound, where there's this nice proof of David Conlin that improves on the upper bound by a factor which is better than polynomial in n. So it's a little bit more than polynomial in n, but still we have these exponential constants of 2 to the half in the exponent here and 2 here. And they've remained the same for now basically 70 years. And so although we have these big gaps here, our understanding for hypergraph Ramsey numbers is even worse. So let's see what happens for triples. So this is a theorem of Erdős, Heinel, and Rado. R3 of n is at most 2 to the 2 to the c prime of n. C and c prime are absolute constants that are positive, and lower bound is 2 to the cn squared. So if you color the triples and you want a monochromatic with two colors and you want a monochromatic little n set, the lower bound right now is still exponential in n squared, and the upper bound is double exponential in n.
These are also two different papers, like two subsets, right?
Yes, so Erdős and Rado proved the upper bound in 1952. This is just a random bound. And so this is what falls out of the random bound. So I should say, yes, this is really Erdős-Rado, but Heinel comes up in a minute. Right.
So the lower bound is a simple probabilistic method.
Yeah, so you just color at random. There's a couple different proofs, but if you simply do it at random, you'll get a bound of this sort. Actually, I want to say this as Erdős, Heinel, and Rado, but it's over 2 papers, and it took more than a decade between them. And then, so for general K, you have a tower of height k minus 2. Rk of n is at least that, and at most a tower of height k minus 1 in C prime n. So you have, so the upper bound, again, is this Erdős-Rado proof, and he has this way of stepping down 1 in the uniformity, but you gain 1 exponential each time. And Erdős and Heinel have a way of stepping up in the uniformity, and this was done in the 1960s, and gaining 1 exponential each time. And so it's really crucial to close the gap here. This is basically single exponential, the lower bound. The upper bound's double exponential. There's a huge gap between these. And we'd like to close this gap. And understanding the gap here that you get for all k is equivalent to understanding for 3 because of the techniques developed here that go up. So this case of k equals 3 is crucial. You color the triples, and you want to understand the bounds. So I should define the tower function. T1 of x is just x. T2 of x, tk of x is 2 to the tk minus 1 of x.
Is your last statement?
So maybe t0 of x. Let's see. Yes. Thank you. Yeah, t0 of x. Yeah, sorry.
Your last statement that the general case will follow from
The 3 case, yeah. So that's a mathematical statement, yeah. So the stepping up lemma and allows you to really get one exponential each step going up in uniformity, starting from 3 to going up to 4 uniform. You would get as a lower bound, and this Erdős-Rado upper bound technique allows you to go down 1 at each step to bound by 1 more exponential, Rk in terms of k minus 1 uniform. And it's a clever pigeonhole argument, this Erdős-Rado upper bound. The very naive argument you would get starts going up in the Ackermann hierarchy when you start proving this. So this is pretty clever idea of Erdős and Rado. And the stepping up is also a very clever idea that they had. What happens? So there's a conjecture that they made. And Erdős offered $500. It's still open. Erdős, Heinel, and Rado that R3 of n is 2 to the 2 to the theta n. So Erdős, Heinel, and Rado believe that the upper bound is really the right answer, that there should be some lower bound construction that matches the upper bound. Why did they think that this is the case? Well, if instead of using 2 colors, you use L colors, or where L is 4. So you can define the L color Ramsey number. We just change 2 to L. They show that that is, in fact, double exponential. So this is Erdős, Heinel, and Rado. R3 of n4 is double exponential in n. And when you look at the upper bound proofs, there are all these pigeonhole arguments, and it really doesn't affect qualitatively the bounds. It changes constants if you change the number of colors from 2 to 4. And yet here you can, the lower bound, you can get a matching construction. Again, it's the stepping up technique, but when you go from 2 to 3, you really have, you don't have enough room, and so you have to double the number of colors from 2 to 4 in the proof. So this is what they proved, and they conjectured for 2 colors it should just be double exponential. Erdős and Heinel were interested in what happens for 3 colors, and they could get an improvement on what they had before. They could prove it's at least 2 to the cn squared times log n squared. This was improved by David Conlin, myself, and Benny Sudakov, where we proved that R3 of n3 is bigger than exponential in any polynomial in n. So R3, n3. So when you allow 3 colors, you get at least 2 to the n to the c log n. It's an exponent. And this is by a variant of the stepping up technique. OK. So we'd like to understand this conjecture. Now, there's a variant of these questions. Instead of getting a monochromatic set, what if you just want an almost monochromatic set, or even just some discrepancy? So you have, say, you 2-color the edges of a complete graph, and you would like a large set where there's substantially more in one color than the other color. Well, if you consider a random coloring, red-blue coloring of the edges of Kn, you give an epsilon, and there's going to be a c of epsilon such that, so with high probability, a random coloring will have the property that every subset of size c of epsilon times log n, the density in each of the 2 colors is about a half up to epsilon. So it's close.
Now you're talking about graphs.
For graphs, so you color the pairs. So for graphs, and the largest monochromatic set is also on the order of log n. And so for graphs, there's not a really big difference between getting a set that even just has a little bit of discrepancy and getting an entirely monochromatic. It's within a constant factor of the size. And so Erdős and Heinel were quite interested in what happens for hypergraphs. And they asked the following question. So this is Erdős and Heinel. For all epsilon greater than 0, does there exist c of epsilon greater than 0 such that every 2 coloring of the triples of an n set have a set S. This is a subset of size little s equals c of epsilon root log n, such that all triples, such that at least a 1 minus epsilon fraction of the triples in S are the same color. It's a question. So this is a question of Erdős Heinel. You'd like to know, can you find an unusually large, almost monochromatic set? Square root of root log n is the inverse of this 2 to the cn squared bound that we had. can you find this large set that's almost monochromatic? And Erdős said that he'd start to question this conjecture. So he originally felt strongly that this should be true, and he said he'd start doubting it if this question has a positive answer, because of the intuition from graphs that they're roughly the same, the almost monochromatic as monochromatic. So with David Conlin and Benny Sudakov, this question is now a theorem, and it's even true for L colors. So this is C of epsilon and L. So even when you L color, you have to get a subset which is at 1 minus epsilon fraction are all the same color of this size square root of log n. And so for L is 4 colors, you get this huge, almost monochromatic subset of size on the order of root log n. On the other hand, the largest monochromatic you can guarantee is only log n. And so it shows for 4 colors that the answer to this problem is very different to the question for monochromatic. So even though for graphs they're roughly the same size, for hypergraphs this is a very different problem. And so Erdős's reasoning for doubting this conjecture is questionable. And so one shouldn't think that because this question of Erdős had a positive answer that one should start doubting this problem. The proof of this is a variant of this Erdős-Rado stepping up with some Turon type estimates as well along the way. OK, so there was this reason, it seemed, to doubt this conjecture, but then that reason to doubt it turned out to be questionable. Now, next thing I want to tell you about is some real reason why you should start to doubt this conjecture. But before I do that, I want to just say a quick strengthening of this statement. So Erdős wanted to know if here you get a 1 minus epsilon fraction, can you find a hypergraph that you get monochromatically, that you don't just say 1 minus epsilon fraction, but some particular hypergraph you get monochromatically. So, if H is a k-uniform hypergraph, so the edges are k subsets, the hypergraph Ramsey number RHL is the minimum big N such that every L coloring of, this is the complete k-uniform, this is an edge coloring, so you color all the k-tuples of a N set, contains a monochromatic copy of H. And our proof of this theorem actually shows something stronger, that the Ramsey number of the blow-up of KD3. So this is a complete d-partite 3-uniform hypergraph with n vertices in each part. So that means you have d parts of size n, and any triple that has vertices in different parts are an edge. And what we show is that the L-color Ramsey number of this is at most 2 to the L to the 2r n squared, where r is the Ramsey number for graphs of d minus 1 and L. And the important thing here is that this is some constant depending on the number of colors and d. And when you let d be large enough, say bigger than 3 over epsilon, then this is almost complete. More than a 1 minus epsilon fraction of the triples will be in such a hypergraph. And so this is tied up to this constant factor depending on L and D in front. And this you can show by random coloring. OK, so that's a strengthening. It was a question of Erdős that we. This is David Conlin, Benny Sudakov, and I. And it uses this Erdős-Rado technique. OK, now I want to look at another hypergraph that people have been considering before. It's called the Hedgehog, although I think we named it the Hedgehog H sub t. It's a 3-uniform hypergraph. 3-uniform hypergraph. The vertex set is the numbers up to t plus t choose 2. And for all 1 less than or equal to I, less than j, less than or equal to t, there exists a unique h which is bigger than t such that I, j, h is an edge. This is the Ramsey number. Yeah, so this is not this R. This is the Ramsey number. So up here, this is you should be putting in the Ramsey number for getting a d-1 clique. Because we have this R and this R, is that the problem? So just in your mind, put this in up here, and then it'll be OK. OK. Yeah, maybe it's not the best. There's a lot of R's, but sometimes we like to use that. OK. Maybe the best thing to do is capital R here to distinguish between the two. OK, thanks. OK, so this hedgehog hypergraph, you have these t vertices. And for each pair of vertices, there's going to be unique third vertex that's outside of those t vertices that makes an edge. And those are your edges. So you have t choose 2 edges, and you have t plus t choose 2 vertices. This is the hedgehog hypergraph. And what can we say about the Ramsey number of the hedgehog hypergraph? Well, this is a very sparse hypergraph. So this is a theorem with David Conlin and Vojta Rudl. R3 of ht with 2 colors is less than or equal to 4t cubed. So it's only polynomial, which is maybe not surprising because it's such a sparse hypergraph. On the other hand, R3 of ht with 4 colors is at least exponential in t. And so it shows that, at least for these hypergraphs, there's actually a significant difference between the 2-color and 4-color Ramsey numbers. And so for 3 colors, we get it's at most t to the c log t. And I'll come back to these different things later. I'll try to explain to you how the proofs of these things work, at least these two. So this looks surprisingly similar to what we were seeing before, except just 1 exponential less. So there's no direct relationship that we've found between these Ramsey numbers and the classical complete Ramsey numbers. But it's so suspicious now in terms of that they look so similar that maybe we really should start doubting this conjecture, that there are hypergraphs where the Ramsey number really does change between if we change the number of colors. OK, so these aren't so difficult to prove. Let's start with the first one for 2 colors. Now, we have a coloring of the triples with colors red and blue. Now let's make an auxiliary coloring of the pairs. We'll color a pair of vertices red if it's in few red triples, say less than t plus t choose 2. Okay, so we have a coloring of triples, of the triples of an n equals 4t cubed set. Color a pair I u v red if so we have a red-blue coloring, and we color a pair uv red if it is in less than or equal to less than t plus t choose 2 red triples, red edges in the hypergraph. I'll call it triples. And blue similarly. So now we have a coloring of the pair of some pairs. If you find a subset of size t with no red pair, then you can greedily make a hedgehog out of it. So if you find such a subset, you're in good shape in terms of creating this hedgehog. Now, here's a key observation to prove that. If you have a vertex v, and it's in a lot of red pairs, and it's in a lot of blue pairs, so these are all red edges, and these are all blue edges, well, it can't be in a lot. It can't be in bigger than or equal to 2t squared red edges and bigger than or equal to 2t squared blue edges in the auxiliary coloring. And the reason for this is consider the edges going across. So you have these, so you consider the triples that contain V, one of the vertices from the red and one of the vertices from the blue. Now that triple has to be red or blue. And so you get either a lot of red triples amongst these or a lot of blue triples. On the other hand, if you count with V a vertex from your red triples, for your red pairs, plus one of these, you see that there are not too many red edges. And if you start with a vertex here and one of the vertices from the blue and add a red one, you see from that direction that there's not too many blue. And because of how you choose the values, you get a contradiction there. OK, so you can't get, in the auxiliary coloring, at least 2t squared red edges coming out of a vertex and 2t squared blue vertices. So each color, you get at most 2t squared in either red or blue. You can throw away half your vertices, and you can just assume, without loss of generality between red and blue, that each vertex is in at most 2t squared red edges in the auxiliary coloring. Now you just need to find an independent set in the red graph, this auxiliary graph you have. And because you have a bound on the degree, it's at most 2t squared. By Brooks' theorem, you can find an independent set of size t, and then you complete the proof. So that gives you the upper bound for R3 HT2. What about for R3 HT4, this exponential lower bound? So there exists a four-coloring of the edges of the complete graph. So now we're just coloring pairs such that, so n is here 2 to the ct, such that every t set has all four colors inside. How would you do this? You would just randomly color, and you show with good probability each of the four colors will appear. This is basically the same proof as Erdős's exponential lower bound on Ramsey numbers. Now we have to color the triples, though. So what do? For every triple, there's 3 pairs that we have inside. There's at least, we have 4 colors to use. We'll use a color that's not inside any of those pairs. There are none of those pairs. So color each triple a color not represented on its pairs. So if you have the colors 1, 2, 3, 4, and you have a triple and it made 1, 2, 3, you would color it 4. Or if it was 1, 1, 2, you have a choice of 3 or 4 to use. Now, if you had, so you always have a choice of what to color a triple, so you have a coloring of all of the triples of this n set this way. And if you had a monochromatic hedgehog, let's look at the body, which are those t vertices, and say it was in color 1. You had these 4 colors. You had this monochromatic in color 1 hedgehog. Well, we knew there was a pair inside in this coloring that got color 1. But then we know that any triple containing that pair can't be color 1. So you can't extend it to a triple. And so therefore, this is not going to be a monochromatic hedgehog in color 1. Is that okay?
So we have a hedgehog, and we assume that it's colored 1.
It's color 1. And so we look at the t vertices where every pair extends to a triple. And we know that in the underlying graph coloring, every t set has all 4 colors. So therefore, there's going to be an edge in that coloring that has color 1. Now that pair is in no triple that's of color 1. Because the way we chose the triple coloring, it has to be a color that's not represented on its pairs. OK, so you can directly tie the 3-color Ramsey number of hedgehogs to a special case of the multicolor Erdős-Heinl conjecture for graphs, which is kind of a very interesting connection, I think. So one of the things we like to see is whether or not this 3-color Ramsey number is polynomial in T, the number of vertices. And so a claim, or a theorem, R3HT3 is equal to T to the big O of 1 is equivalent to the multicolor Erdős-Heinl conjecture. The Erdős-Heinl conjecture is a famous conjecture in graph Ramsey theory. So it's about graphs, and there's a multicolor generalization for 4 colors, 1, 2, 3, 4, forbidding a 1, 2, 3 triangle. So I'll explain what the Erdős-Heinl conjecture is. The Erdős-Heinl conjecture, so whenever we have a graph on n vertices, it always contains a Clicker-independent set on the order of log n, and this is best possible. This is what we basically started with. If you forbid an induced subgraph, like a 5-cycle, you fix an induced subgraph that you forbid, so that means you don't have a 5-cycle with all the non-edges missing as well inside your graph, then it's generally believed that the graph should be much more structured. And the Erdős-Heinl conjecture says something of this sort, that there should be a much larger Clicker-independent set. Instead of log n, you should get n to some power, epsilon, that depends on your h that you forbid. There's a multicolor version of this. So if you think of the edges as being one color and the non-edges as being another color, that's a 2-coloring you're looking for of a complete graph, where there's a particular missing coloring of that's a fixed size of a complete graph, a small complete graph, and you'd like that there to be a missing color on some large subset. So the natural generalization turns out to be that you have some R coloring of a complete graph, R edge coloring, and you have some fixed forbidden R coloring of a small complete graph with the same R colors, and then you should be able to find a large subset of vertices that misses one of the R colors. And that large subset should be n to some epsilon, depending on this small forbidden thing you have. So one thing you can ask, and this was a question of Erdős, not of Erdős, it was of Heinl. Heinl asked if you use 3 colors and forbid a 1, 2, 3 triangle, a rainbow triangle, how big of a clicker-independent set, not clicker-independent set, but two-colored set must you have? So you three-color the edges of a complete graph. You forbid a rainbow triangle, all the edges are different. How big of a two-colored set must you have? And with my student, Andre Grinspun, and with Janos Pak, we showed that the answer turns out to be within a constant factor of n to the 1/3 times the square of log n. And n to the 1/3 is pretty easy using perfect graphs, and you also have to use two applications of a weighted version of Ramsey's theorem to get the extra log factors there. And then we generalize this in various ways, but and it became a long, difficult paper to prove these generalizations with a number of log factors. But one thing we couldn't do was this case of you have 4 colors, 1, 2, 3, 4. You color the edges of a complete graph with these 4 colors, 1, 2, 3, 4. And you're only forbidding a 1, 2, 3 triangle. Then you should be able to find a large subset n to the epsilon size. So you have a coloring of a complete graph on n vertices with 4 colors. You should be able to find an n to the epsilon size subset where one of the 4 colors is missing. And that's equivalent to this being polynomial.
That's false, is what you are saying.
No, we don't know this. We just know an upper bound. We don't know a lower bound. Yeah, yeah. So there's a direct connection between these. And
Is there any connection between the usual Erdős-Heinel and the multicolored Erdős-Heinel?
it's a special case. It looks like if you could prove Erdős-Heinel, probably the techniques would generalize. But I don't know that it's equivalent. Yeah. Yeah, I don't know equivalence. That would be interesting. OK. So we've been talking about graphs and hypergraphs. Are there any questions about this before I turn over to words? Some of us like words. There are lots of languages and things people study. No questions. OK. So let's look at Ramsey theory for words, which is something I really hadn't thought about until a couple of weeks ago. And this is a new project recently with David Conlin and Benny Sudakov. So Ramsey theory on words. So let W be a word in letters x1 to xn. These are your x sub q. Sorry, x sub n. An instance of W is any word of the form W of U1, U2, UN, where these UIs are words. So let's see an example of this. So let's look at the word mathematics. And I claim this is an instance of x, y, x, z. So I could take mat and I see, oh, that's repeated twice. I'll make that my letter x. And HE will be my y, and x will be my z. And so mathematics is an instance of x, y, x, z.
Your words are never empty.
What?
The words are never empty.
The UIs are never empty, yeah. Yeah, so they should have at least one letter. Yes. W is Q of unavoidable if every sufficiently long word over a Q letter alphabet, so an alphabet with Q letters, contains an instance of W as a subword. And by a subword, we mean an interval. So some interval of letters. So athemat is a subword of mathematics. It has to really be an interval of letters. You can't just take a subsequence. And you should get an instance as a subword. OK, so that's Q unavoidable. Otherwise, it is Q avoidable. Avoidable. And it's W is just called unavoidable if it is Q unavoidable for all Q. So these are for all positive integers Q.
So
Yeah.
W is in some alphabet too,
Yeah, W is in some alphabet.
which is a subcase of the Q letter alphabet.
It could be anything.
Then I don't understand.
So there's this substitution here, right? So here, W would be, in this example, W is X, Y, X, Z. And mathematics would be an example of W. So it contains an instance of W.
Oh, you can substitute, I see.
Yeah, so it's based on this substitution into, so you substitute in words. And so when you write this word out where you substitute these subwords, and so it can be an entirely different alphabet than what you're looking inside of. So so let me give a couple more, another example. So here's another example. XX is 2 unavoidable. XX is saying that you have two identical strings. You have two subwords, one after the other, that are identical somewhere in your word. If it has an instance of W as a subword, then you have, so this is W, you should have what they call a square in it.
So XX is 3 avoidable.
So XX is 2 avoidable. Yeah, so XXX is 2, and XX is 3, right. So, but 3 avoidable. And so the 2 unavoidable, well, if you have 2 letters that are identical next to each other, you already have a copy of W. So it has to alternate. So if it starts with 0, you get 1, then 0, then, already at 1 after 4 letters, you get 0, 1, 0, 1, and you get 2 squares that are next to each other. You get a square, so you get 2 copies of something next to each other. But it's 3 avoidable, and this is a theorem of Axel Thu from 1906. It's a very classical result. There are a number of books on this whole area of combinatorics on words, and this is one of the basic facts in this area. There's been a lot of research on this in this area. So what are the unavoidable words? What?
Where does the proof come from?
Yeah.
Of this?
Yeah, which area is that?
It's just some recursive construction. So words come up in many different areas. It comes up in group theory, as you know. You've done some very nice research on that. And it also comes up in topology and algebra and number theory and combinatorics. And
Yeah, but the proof is very
it's very simple. You can do this recursive substitution. Yeah. Okay, so what are the unavoidable words? There's this Zeeman words. So Z1 is x, Z2 would be xyx, Z3 is xyx, zxyx, ... So you make two copies of your previous word and then stick a new letter in between. So you can formally write that Z1 is x1, say, and Zn is Zn minus 1. You stick in a new letter, xn, and then you put the same copy of Zn minus 1. These are the Zeeman words. They come up in a number of places. One way you can see that, look at the order of 2 in the first 2 to the n minus 1 positive integers. It makes exactly this Zeeman word. And so you get 0, 1, 0, 2, 0, 1, 0, 3, 0, 1, 0, 2. The largest power of 2 that divides the number. You get exactly this Zeeman word. This Zn has length 2 to the n minus 1. So Zeeman's theorem from 1982 is that a word W with n distinct letters is unavoidable if and only if Zn has an instance of W as a subword. So it's all about the Zeeman words. These are unavoidable, basically. So it's natural to look at how far. Yeah, so the word W has n distinct letters, and then the Zeeman word you're looking at. Okay, so so a natural question that's been studied is how long do you need, the Ramsey number for this, so before you get the copy of the nth Zeeman word. And Q here, the number of letters, really behaves very much like the number of colors in before. So the size of the alphabet. So FNQ, it's the minimum big N such that every word of length big N has an instance of Zn as a subword. And the question is to what are these numbers? What do they look like? So you can start computing them. F1q is 1. F2q is 2q plus 1. This is because if you want Z2, xyx, it's equivalent to finding two letters in your word that are identical and not adjacent, not consecutive. And so once you have 2q plus 1 letters, then you have 3 copies of the same letter. And so 2 of them are going to be spaced out, the first and last one, and then you get a subword. And then you can just go the letters 1, 1, 2, 2, 3, 3, 4, 4, et cetera, up to 2q to see that that's a lower bound. So Zeeman showed that his proof shows that FNQ is at most Ackermann type. This was subsequently, it's not supposed to be. I mean, it looks like it.
So you get some recursive bound. I mean, we just need.
Right, to see what the bounds are. Exactly. So there's a not so difficult proof that gives f and q is at most, and this is not Zeeman's bound. This is Cooper, Joshua Cooper, and and Rohrbach, they proved, so this should be n minus 1 q, and then q to the fn minus 1 q, and then plus fn minus 1 q. So why would this bound be true? This is the recursive bound you get. So if you look at the first fn minus 1 q letters, you'll have some instance of zn minus 1 in there. Then add one more to get a little bit of space. And then you'll get another instance of zn minus 1 in there. And there's at most q to the fn minus 1 q possible instances you're going to see here. And so two of them, once you get enough, will be the same. And when you get two of them that they're same, they're spaced out, you get a copy of Zn between them. So you can glue those two and whatever you get in between. Now, instead of this, so this gives you a bound of something that looks like q to the q to the q roughly to the 2q plus 1, where this is going to be n minus 1. Q's there.
If you have some
Including the 2q plus 1.
length of maybe you want to have some control of the length of the given words that you get.
Right. So, well, the length will only tell you sort of this much. Really, this is about counting the number of Zeeman words.
Yeah, but if I would know that its length is significantly smaller than fn minus 1 to the q, I would not need to take q raised.
Right. But actually, most of them will be pretty long. But you still don't get too many of them. So you can replace this by the number of minimal Zn minus 1 containing words. And if you do that, you can count those pretty easily for the first case. And instead of getting this, you'll get basically q, and it's q minus little oq. And so that observation was put in a paper by Ritter and Schur, that you can replace this by counting them. But more or less what Noga is saying, that you can improve on this bound. But, OK. Now, what about lower bounds? Cooper and Rohrbach considered randomly distributing the letters. And so this is Cooper and Rohrbach. And through randomly coloring random sequences, they get a lower bound, which is q to the 2 to the n minus 1 times 1 plus little o1, as long as q and n tend to infinity in their proof. OK, so that's a polynomial in q, double exponential in n bound. And our upper bound is this tower of height n minus 1 in q. So the question is, what is the answer between these two? So the theorem is that fnq is, in fact, the upper bound, that it equals this up to this little oq. And this is with David Conlin and Benny Sudakov. And this is as long as q is substantially bigger than n, which is bigger than 3. So we're running out of time. Let me say that the proof of the lower bound, you can use the Lovász local lemma. It's not the most straightforward way of doing it, because you can't just consider a uniform at random. You have to pick the random distribution in a careful way. But once you do that, you can use the local lemma and get this bound. For 3, it's not so bad. For higher, it gets more complicated. There's also a way to, instead of using the local lemma, you can step up. And instead of looking at the length of the longest, you look at the number of those that you get that avoid. And you get basically a factorial more in each time you step up in n, but then you have to add 2 letters at each step. It's kind of similar to what's going on in what we saw earlier with these hypergraph Ramsey numbers, that if you add more colors, it becomes helpful.
So the local lemma, you apply iteratively or you apply it once?
You can apply it once, but you have to keep control of all of these bad events at the same time. So and there's different types of bad events, and so it gets a bit complicated. But there's a constructive proof starting with going from n equals 3, that's quite nice, upwards. And you get 2 more letters at each step. And you get a factorial many more of these things. And just through counting, you get that there has to be long ones. So there's an alternative proof. And then it's a very, it's an interesting question about what happens with 2-letter alphabets. It's very similar to what we were seeing with hypergraphs. What if q equals 2? So we want to look at fn2. We look at binary strings, and we want to avoid fn2. Well, for that, if you start looking at the first few values, for 1, you get 1. For 2, you get 5. For 3, you get 29. This is in the Cooper and Rohrbach paper. They computed these all out. For 4, you get at least 10,483. So what happens here? Now, even this bound doesn't apply because they're assuming q and n tend to infinity there. So we have no lower bound at this point on fn2. I mean, it's at least 2 to the n minus 1 because you have to get a copy of zn in there, and you need enough letters. OK, so what's the answer? The answer turns out to be it's a tower of 2's of height n up to an additive constant. So again, David Conlin, Benny Sudakov, and I, fn2 is a tower of 2's of height within an additive constant of n. Now, the proof is inspired by the proof of this, except there you're adding 2 new letters at each stage. So how do you go between sticking with 2 letters and going up? Well, instead of adding new letters, you can make long words that behave like new letters. So you make a string of 1's of length 2n that will behave as if you made a new letter, because the previous ones you'll have forbidden that length. And you put that in, and you make every word that you started with start and end with a 0. So whenever you see this 1, 1, 1, 1, 2n times, you would think that that's your new letter that you added in. And so that's the idea, is to use words inside that behave like new letters, longer words that behave like new letters. And you can use that and get this bound. It takes several pages because you have to consider chopping off these strings of words so it doesn't cut off perfectly. And so you have to be very careful about ends and doing things with that. So the hour is basically up. And while only halfway through the talk, I thought I would end here. Thank you.